Okay, we're going to jump into Chapter 7 now. You've already done a little bit of homework on this material, but I wanted to give you guys a video on it as well. So we're going to start with Chapter 7.1, which is all about exponential growth. And then we'll get into Chapter 7.2, where we start talking about exponential decay, which is something maybe a little bit less comfortable. So here's the basic idea of exponential growth. An exponential growth model is where I have y equals a number raised to a power. Okay. The difference here is that a polynomial has the exponent, the variable in the base, and the exponent is a constant number. This is a polynomial. An exponential function, the base is a constant, and the exponent is the variable. Okay. So the exponent is changing. Okay. This particular picture here that I've got here, this is y equals 2 to the x. Okay. So the idea behind this is we're looking at something where we start with when x is equal to 0, we can create a t-table, right? I'm going to go up down here, I'm going to make a t-table of x versus y, 0, 1, 2, 3, 4, let's go up to 4, we're ready to go much further. And notice we can go negative as well, so maybe we should do negative as well. But let's start with just positive numbers to get a sense of what this is. This is 1, 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. Okay. So what's happening? As we go up the ladder, we end up multiplying by 2. And as we go down the ladder, we end up dividing by 2. And you can see that's exactly what's happening here. If I start at 1, next one will be 4, then 8. And it goes pretty quickly. If I go the other direction, a half, a quarter, an eighth, 16th, and so on. Okay? So going to the right doubles, and going to the left halves. So that's what this is. So this 2 to the x function here, I'm going to go ahead and erase some of this here. What can it represent? Well, it can represent anything that when I move forward in time, it doubles in size. So populations grow this way, right? If you have, if we kind of forget about the problem of inbreeding, right? If we have a population of, let's say, 2, size 2, okay? Suppose that in a population of size 2, okay, every year this population, whatever the population is, maybe it's bacteria, maybe it's some kind of mammal, who knows. Every year they have 2 offspring. Every 2 have 2 offspring. That means that in 1 year they'll have 4 total. Okay. Now I have 2 sets of 2. Okay. So now each set of 2 can produce 2 more. So it's going to double. Now we're going to have 8. Now we have 4 sets of 2. And that can double now, and we have 16. So anything where, depending on what we had before, we then take twice as many, that's an exponential model. Okay. So population growth is a typical one, and interest are the 2 that you see. So population growth, okay, and interest, when we're talking about banking, right? So population growth and interest are the 2 main applications. Yeah. So let's look at a slightly more complicated model. Okay. This model here is a little bit different. The way we're going to graph this, and I've shown you the graph already, the way you want to graph this is again with the t-table. X, Y. In general, if you don't know how to graph something by hand, you want to use a t-table. Okay. So if I put in, let's start with the 0 because it's going to be much easier. Okay. 0, -1, so it's going to be 2 to the -1, so 2 minus 3 is -1. Okay. And then we're going to get 1. It's going to be 4 minus 3 is 1. Okay, so we have -1, 0, -1, 1, 1. Okay, I'm guessing 2 is going to go to, what, 4? Let's see. 2, 8, 5. Okay. So we have the same kind of relationship, right? 2, 4. The next one would be up a difference of 8. So this should be 13. Okay? And so on. So 3 should go to 13, and we're going to see that. Notice the difference is going up double. Okay. All right. So let's take a look at this now. What do we know about this? Well, this is the same basic picture as before. It's the same basic shape where it starts off very small and never goes below 0 in this case, and shoots up to something very, very big after passing through this point right here on the x-axis, on the y-axis. The same thing is happening here. It's really the same basic picture as the b to the x, except that it's been shifted down 3 units, to the right 1 unit, and it's been stretched by 4 units. So whenever you're looking at these exponential models, this is the same as b to the x, except that the number a stretches the picture, the number h moves the picture to the right, and the number k moves the picture up. Okay, we're not going to spend a lot of time on this, but this is how we're going to graph these things by hand if we ever need to. Okay, so we're going to look at an example here of putting money in the bank. So we start with $10, and every month we're going to get 2% interest on that. That means at the end of the first month, I'm going to have 1.02 of 10. Okay, why 1.02? Well, 10 times 0.02 is going to be 20 cents. I want 20 cents plus what I already had, plus the 10. So I want 10 times 0.02 plus 10. I can factor out a 10, and I'm left with 10 times 0.02 plus 1, which is 10 times 1.02. What this does is says not just 20% of, not just 2% of 10, but 2% of 10 plus 10 back. Okay? So I'm going to end up with, at the end of the first month, I'm going to end up with $10.20. Okay? Now, what's interesting about this is that at the end of the second month, I started that month with $10.20, so I'm going to get 1.02 of $10.20. So at the end of the second month, I'm going to end up with 10.2 times 1.02. I'm going to end up with $10.40, 40.04. Okay? So 40.4 rather. So 10.404. Okay? So instead of taking 10% of 2% of 10, sorry about that, which is 20 cents, instead of simply starting with that and taking 20 cents 12 times for 12 months and ending up with $2.40, okay, instead of ending up with $10 at the beginning of the year plus $2.40 interest, okay, I end up with a little bit more because every time I deposit the 20 cents back into the bank account and I get 2% of that as well, okay, and then I deposit that back in, and so it builds exponentially. Okay, so what I do is I start with $10 rather. I start with $10 and I multiply 1.02 times 10 12 times. Okay, so here's what I end up with. Instead of ending up with the $10, the $12.40 here, I end up with 10 times 1.02. Whoa, what happened here? 10 times 1.02 raised to the 12th power. So I end up with $12.68. versus this, which would have been $12.40. So I end up with 28 cents more than I would have if I hadn't deposited those 20 cents into the bank account every month. So here's what I do. Okay, in a situation like this, if I have a rate and I know that my whatever it is increasing by that rate, in our case our rate was 0.02, I can use this formula to figure out what we're going to have left at a particular time. This works with money, it works with any kind of population. So y is going to be what's left at the end of the period. A is however much you start with. Okay, that goes here. The rate is whatever rate is given in the problem, and the times how long we're looking at. So in our case, we had y equals our initial deposit times 1 plus our rate, which was 2%, and we did it 12 times. Okay. All right. Let's look at another situation. This is called compound interest, and this is specific to a financial situation. Okay, and you need to make sure you have this down in your notes. Here's a typical compound interest equation. These are letters that we always use. A equals capital P, parentheses, 1 plus R over N to the NT. So A is going to be the amount at the end of the period of interest. P is the principal amount, or initial amount. That's the amount that we deposit at the very beginning of the investment. N is a new number. N is the number of times compounded per year. And T is the time in years. Now the reason we have to set this up is that most of the time, if you look at an interest rate, maybe they say it's a 3% APR. Okay. Now, 3% is annual. Okay. All rates when you're talking about banking are considered annual rates. Okay. It's the amount over a year that you can earn on an investment. So rather than saying, hey, this is a 2% monthly rate, every rate is expressed as an annual rate. Now, what's weird about this is that you actually get different answers depending on how often you compute the interest. Okay, so we're going to look at this. Let's take a look at a problem, see how this applies in practice. So suppose we deposit $4,000 into an account that pays 2.92% of annual interest. Let's find the balance after 1 year for an account that compounds quarterly and daily. So let's start with quarterly. Okay, so we're going to look for the amount, and we'll write the equation down. I always write the equation down like this without even plugging anything in, because I know that this way on an exam I can get some credit for that. Okay, so this is what we're going to look for, is the amount. The amount is going to be equal to, for part A, our initial investment times 1 plus our rate, and our rate needs to be a decimal, 0.0292, divided by, we're doing this quarterly, so that means 4 times per year. N is 4, and we're doing it for 1 year. So this means that we crunch the numbers, we crunch that compounding rate 4 times a year instead of every day, okay? And we do that for the entire year, okay? So here's what it's going to look like. We're going to have $4,000 times 1 plus 0.0292 divided by 4. And we have to divide by 4 because it's an annual rate, and if we're compounding 4 times, we have to take that rate and divide it by 4. Raised to the 4 times 1. I could just do 4 here. Okay, and I'm going to end up with, at the end of the year, $4,118.08. 4118.08. Okay, and I'm assuming the bank is not going to round that cent up for us. Okay. Part B says let's do the exact same thing, but now we're going to do it daily. Okay. So we're going to take that same initial investment, and we're going to compound it, same rate. We're going to do it every day of the year. Okay. So we're going to do this 365 times, but every time the rate is very, very small. Okay? Whereas here we did it 4 times, but every time here the rate was relatively larger. Okay? So which one should we do? Okay? Should we compound a smaller rate many, many, many times, Or should we compound a larger rate fewer times? Let's see. Okay, so we'll start with $4,000. 1 plus 0.0292 divided by 365 raised to the 365 times 1. I'm not going to do the 1 this time. I get $4,118.51. 4,118.51. Okay, it's not a huge difference, but it is a difference. Okay, this same annual rate, okay, depending on how often you calculate the interest, ends up with different amounts in the account at the end of the year. Okay, so just something for us to remember. Now, of course, this is not a huge difference. Okay, but what if you had $40,000? Okay, you'd be making a decent amount of money. What if we look at this over 5 years? Okay, it's going to start adding up. Okay, so we're going to be looking at more examples in class. Thanks.